Welcome to lecture number 11 for ECE 211, Circuits 1. In this lecture, we're going to look at Thevenin equivalence with dependent sources and max power transfer. Now, recapping, in the last lecture, we looked at Thevenin and Norton equivalence. What that is for any linear circuit, the voltage versus current is going to follow a straight line. If there is no current flow, I'll tend to have a maximum voltage. As I reduce the voltage, I get more and more current following a load line. I can also think that as a resistance. The slope right here would be the resistance. At this point, R is infinity. When I have infinite resistance at the load, I'll have the open circuit voltage. At this point, I have a short. The load resistance equals 0. And the slope would be some other resistance. As I vary the load resistance, the voltage current will follow a straight line. That's your load line. Now, any circuit that has the same load line behaves the same as far as the load is concerned. The simplest circuits for a given load line would be a voltage source and a resistance. That's called the Thevenin equivalent. Or a current source and a resistance. That's called the Norton equivalent. In the previous lecture, we looked at how to take a circuit and convert it to a Thevenin equivalent or Norton equivalent. In this lecture, we're going to look at finding the Thevenin equivalent when you have a dependent source and find the load that maximizes the power to the load. So for dependent sources, there's a couple different types. You'll talk about these more when you take electronics. If you have a current-controlled current source, that's actually a BJT transistor, a topic covered in electronics. If you have a voltage-controlled voltage source, that's typically an op-amp circuit and amplifier. If I have a voltage-controlled current source, that would be a MOSFET. So all these are devices you talk about in electronics. That's a different class. In this class, we're just going to use these as dependent sources, how to analyze that circuit, where they come from, you'll cover when you get to electronics. For here, just treat that as a circuit element. So let's start out with a current-controlled current source. Again, this is a BJT transistor when you take electronics. For now, it's just a circuit element. Okay? Suppose I have this circuit. Find the open circuit voltage, the short circuit current, and the Thevenin equivalent. So being a linear circuit, I know it's going to look like something like this. If I call this Vx, I have a resistor over here, and that's Ix. I know the load line is going to look like this. What are these 2 points? That's the short circuit current. This is the open circuit voltage, and the slope, voltage over current, is resistance, R Thevenin. So let's find that. Starting out, let's find the open circuit voltage. Well, that's just a circuits problem. For this case, it's probably easiest using voltage nodes. I know that V0 is 5 volts. I know the currents have to balance at V1. So V1 minus V0 over 3K. Well, let's do it this way. IB is V0 minus V1 over 3K. At node 1, the current left, that's minus IB, plus this current, minus 100 IB, plus this current, V1 over 5K, equals 0. 2 equations, 2 unknowns, solve. When you solve, you're going to get V open is 4.9705 volts. So on the load line, that's this point right here. That's 4.97 volts. Next, let's find the short circuit current. Take the circuit and short it to ground. Now find this current. Well, by observation, V1 equals 0. I just shorted it, so this current is 0. Currents have to balance. IB is just 5 minus 0 over 3K. IB is 1.6 milliamps. At this point, the currents balance. So minus IB minus 100 IB plus I short equals 0. Solve for I short, and I get 168 milliamps. So on my load line, I have my second point. This is 4.97 volts. This is 168 milliamps. That's really all you need. Given 2 points, I can find the slope. To to find the Thevenin resistance, I could just take the ratio. The ratio between the open circuit voltage and short circuit current is our Thevenin, 29.5 ohms. That's one way to do it. Second problem. If I just asked you what is the Thevenin impedance, I could do two problems, find the open circuit voltage, short circuit current, take the ratio. That works. Can I find it directly? Well, to find the Thevenin resistance, what I do is I turn off the sources. Again, think the Thevenin equivalent looks like this. This is your V Thevenin. Here's R Thevenin. To find R Thevenin, turn off the source, make that 0. Do the same thing in your circuit. Take the sources, set them to 0. Now find the resistance looking in. Now last lecture that was pretty easy to do. That's just a bunch of resistors in series and parallel. Now it's harder. I've got that dependent source that kind of messes things up, and I don't really know what to do. If you don't know what to do, add a test voltage. This is actually how ohm meters work. I'll add a test voltage, like a 1-volt source, and calculate how much current does it draw. Then the Thevenin impedance is just voltage over current. Our Thevenin is 1 volt over Ix. That's one way to find it. But here I only have to do one calculation rather than two, so maybe it's easier if that's all I want. So let's find Ix. I know that V0 is 0. At V1, currents have to balance. So this current is, well, IB is 0 minus V1 over 3K, minus IB minus 100 IB minus 1 over 5K minus Ix, or E is equal to Ix. Current in equals current out. So add all this up, I get 33.87 milliamps. I then know the resistance. Resistance is voltage over current. 1 volt draws 33 milliamps. This apparently is 29.53 ohms. So all this mess looks like 29.5 ohms. Not really obvious, but that's what it is. So that's my Thevenin equivalent. That circuit looking in looks like this. This is 29.5 ohms. And I misspelled 29.5. 29.5 and 4.97 volts. This is also where Thevenins are kind of nice. This is a whole lot easier to analyze than that circuit. They're equivalent as far as the output's concerned. So here's a practice problem. Find the Thevenin equivalent, Thevenin resistance of this circuit. Again, I could do the open circuit voltage, short circuit current, take the ratio, or let's apply a test voltage and calculate the current. Let's pause the video and have you try to solve that one. Solving it, I turn off the sources. There are no sources. And find the resistance looking in. I don't really know because that current source is messing me up. So in that case, let's apply a test voltage. I'll apply a 1 volt test. Find the current draw. Then the Thevenin resistance is just 1 volt over Ix. So let's do that. Apply a 1 volt test. I know this is 1 volt. V1 I don't know. V2 I don't know. So currents have to balance at this point. At V2, well, I know IB. IB is 1 minus V1 over 2K at node 1. Minus IB plus V1 over 300 minus 100 IB equals 0. Two equations, two unknowns, solve. I get V1 is 0.93 volts. I know that Ix is 1 over 10K plus 1 minus 0.93 over 2K, 130 microamps. Therefore, the resistance is 1 volt over 130 microamps, 7635 ohms. That's the Thevenin impedance, or the impedance looking in. Again, not really obvious from the circuit, but that's what it is. Let's try another example. Suppose I have this circuit. Find the open circuit voltage, short circuit current, and Thevenin impedance. So let's start with the open circuit voltage. I'll just leave this open, find out what V3 is. To do that, I've got three equations, three unknowns. I know that V2 is minus 1000 V1. I know that V1, current left, is V1 minus 1 over 1K. Current right is V1 minus V3 over 10K equals 0. At Y, current up, V3 minus V1 over 10K. Current left, V3 minus V2 over 100 equals 0. Three equations, three unknowns. Now here you group the terms, put in matrix form, solve in MATLAB. I'm not going to go through all that. Here's what you wind up with. This is what I want. V3 is 9.8901 volts, so that's the open circuit voltage. On the load line, and it's going to look like this. The open circuit voltage is minus 9.89 volts. Next, let's find the short circuit current. Take the output and tie it to ground. Calculate that. So if this is 0 volts, I know that this current is, let's do the node equation V1. V1 minus 1 over 1K plus V1 over 10K equals 0. Solving, I get V1 is 0.909 volts. Once I know V1, I know 1000 V1. Once I know 1000 V1, I can find the short circuit current. It is this current plus that current. That'll be 1 volt over 11K. That's this current. This current is minus 1000 V1 over 100. Add them all up, you get minus 9.09 amps. So there's my load line, minus 9.89 volts. Ugly 9. And minus 9.09 amps. Find the Thevenin resistance. Just take the ratio, open circuit voltage, divided by the short circuit current. This looks like a 1 ohm resistor looking in. One way to do it. Another way is, if I don't want to do the open circuit voltage, short circuit current, just find the resistance directly. I turn off the sources, make that 0, find the impedance looking in, and it's not very obvious. So let's apply a 1 volt test and find the current. Well, if this is 0 volts, this is 1 volt, I can find V1 by voltage division. It's 1 over 10 times 1 volt, 0.09091 volts. That's V1. I know V2 is 1000 V1 minus 90.91 volts. I can now find the current. Ix is this current plus that current. So it is 1 volt over 11K plus this current, 1 minus 90 over 100 gives you plus 919 milliamps. So there's the second point. 919 milliamps, that's the current. So 1 volt results in 919 milliamps being drawn. The impedance is 1.088 ohms. Same answer as before. So either approach works. So here's a practice problem. Find the input impedance looking in. Again, I've got a dependent source, so I don't really know what to do. In that case, I'm just going to apply a test voltage, say 1 volt, and calculate what is the current. So doing that, here's my 1 volt test. By voltage division, this is 1/3 of 1 volt, 1/3 volt. This is 1,000 times that, so it's minus 333 volts. then the current. I've got 1 volt over 3K plus 1 minus 333 over 100 gives you Ix is plus 3.34 amps. The impedance looking in then is voltage over current is 0.299 ohms. So this looking in looks like 0.299 ohms. So that is kind of how to handle when you have dependent sources. A common trick is if you can't tell what's going on, apply a test voltage. Apply the test voltage, find the current, and then the ratio will tell you the input impedance. Just make sure that you turn off the sources. So the voltage sources are 0, current sources are 0, dependent sources still remain. Next part of the lecture. Suppose I've done a Thevenin equivalent. What resistor maximizes the power to the load? And kind of application is if this is a solar panel, the solar panel's got an open circuit voltage, short circuit current, meaning Thevenin impedance. If this is a solar panel, how much power can I pull out of the solar panel? What load maximizes the power? If this is a stereo, my stereo looking in has a Thevenin voltage, Thevenin resistance. What resistance to the speaker maximizes the power to the speaker? That's max power transfer problem. And note there is a maximum. If RL equals 0, power is volts times amps. If I short this, voltage is 0, power is 0. If I open it, current is 0, power is 0. So somewhere between 0 and infinity for resistance, there's maximum power. Find that value of R. So let's take two cases. First, let's look at what happens if R Thevenin is fixed and I can vary the load. So like here's a solar panel, it's fixed, I want to vary the load. How much power can I get out of the solar panel? Well, in that case, the current is V Thevenin over R Thevenin plus RL. Power to the load is I squared R, which is, take this and square it, or I guess it's just volts times amps. So here's the voltage, V Thevenin, here's the amps. Try that again. It's I squared RL, so take I and square it, I missed a square, times RL. Bring these outside and inside. There's the power as a function of RL. I want to maximize the power, so take the derivative with respect to RL. So when I do that, I'll have ho d high minus high d ho over ho ho. And one way to do it is ho d high minus high d ho over ho ho. So the bottom times derivative of the top, which is RL plus R Thevenin squared. So let's take that derivative. That'll be ho d high R Thevenin plus RL squared. There's ho d high minus high d ho. RL derivative of the bottom is 2 R Thevenin plus RL ho d high minus high d ho over ho ho to the fourth power. That's equal to 0. This doesn't matter. We've got to set the numerator to 0. So there is an RL plus R Thevenin. Pull that out. I've got times R Thevenin plus RL minus 2RL. That gives you R Thevenin minus RL times RL plus R Thevenin plus RL. Take the derivative, that's what you get. So that tells you either RL is minus R Thevenin or plus R Thevenin. When it's minus R Thevenin, that's the minimum, it's producing energy. Equal to R Thevenin, that's the maximum, absorbing energy. So there's the solution. I want to set the load equal to R Thevenin. That's one of the uses of Thevenin equivalent. Once I have the Thevenin, I know what load maximizes the power of the load, R Thevenin. And MATLAB can do calculations. Suppose I've got a 12-volt source, R Thevenin is 2 ohms. What's the power to the load when the load goes between 0 and 10 ohms? Steps of 0.05. Well, the current is just voltage divided by total resistance. The voltage is, hard way to do it. Okay, voltage division, RL over RL plus R Thevenin times V Thevenin, or just I times R. Power is volts times amps. Plot it. And here's what it looks like. When the load is 0, there's no power to the load. I get a maximum at 2 ohms. That's when R load equals R Thevenin, and then the power drops off. So max power is when the load matches R Thevenin. At that point, you're at 50% efficiency. Second problem. Suppose instead I've got a fixed load and I can change R Thevenin. Redesign my amplifier. What value of R Thevenin do I want? Well, again, power is that. Got the square term. Set the power to 0, and I want to take the derivative with respect to R Thevenin, wind up with this mess. This doesn't matter. RL is a constant. I want to pick R Thevenin to make this 0. That tells you that R Thevenin is minus RL. So I actually want to have a negative resistance for R Thevenin. That'll maximize the power. Then the power's infinity. If I can't have a negative resistance, make it as close to negative RL as possible, meaning 0. You can see that in MATLAB. Suppose I've got a 12-volt source, 2 ohm load. R Thevenin could be anything between 0 and 10 ohms. Find the current, find the voltage at the load, power is volts times amps, plot it. Here's the power to the load versus resistance. Max power is at 0 ohms. The smaller the resistance, the better. So it's a slightly different problem. Can I vary the load or vary R Thevenin? R Thevenin should be as small as possible. The load should match R Thevenin. Slightly different problem. What resistance at the load maximizes the efficiency? Well, efficiency is power to the load divided by the total power. That'll be I squared RL over I squared RL plus R Thevenin. I squareds cancel, so it's just RL over RL plus R Thevenin. The max efficiency is when RL equals infinity. There I'm at 100% efficiency. When RL equals R Thevenin, I'm at 50% efficiency. So if I plot efficiency versus load for 2 ohm load, here is max power, 50%. Infinity is max efficiency. And you kind of see that there's a trade-off. As to get higher efficiencies, I get less power to the load. So you're kind of stuck. So that's kind of the idea behind Thevenin equivalence with dependent sources and max power. If you have a dependent source in your circuit, the trick to find R Thevenin is apply a test voltage, turn off the sources, and find the current draw. The resistance looking in then is voltage divided by current. Once I know the Thevenin resistance, that tells me quite a bit. If I want to get max power to the load, I want to make our load equal to R Thevenin. However, at that point, I'm at 50% efficiency. And that is lecture number 11 for ECE 211, Thevenin equivalence with max power.